Okay. Now, the example we saw so far is the case of a linear function. That is, the rate of change is a constant. The graph of the function is a straight line. Its derivative will be a constant. Is that right? Because the slope of a straight line does not change. The linear function, the slope does not change. Now, on the other hand, think of a car that starts from rest, then increases its speed for a while, and then applies brakes and slows down and comes to a stop. Now, how does the position x of the car change with time? Now, have you understood the scenario I described for you? A car increases its speed. That is, actually, you are starting from the light changed to green. You put your foot down, the speed increases, then ahead you see a red light. So as the speed increases, you apply brakes, you reduce the speed, and then come to a stop. Now it will look like this. When t equals 0, you are just starting. Now you cover this much distance in the first second, this much distance in the second second, this much in the third second. You can see your speed is increasing, and this much distance in the fourth second, and at the end of the fourth second you see the red light ahead of you. You put your foot on the brake. The distance now, the fifth second the distance is less, the sixth second even less, and so on. Now, how does the graph of x against time look like? You can see as the time interval t equal to 1, this is your x value. T equal to 2, x value is greater. At the end of t equal to 3 seconds, you can see from t equal to 2 to t equal to 3, the distance covered is even greater. So, remember, if the distance covered is the same every time interval, then you get a straight line graph. Is that right? Now, in this case, the graph is going to be curving up, because each time the time increases by 1 unit, the distance is going to increase greater each time. So you can see the graph will curve up. Now, how about here? Each time the time changes by 1 unit, the distance decreases. In other words, the graph will curve down. So if you look at the graph I have drawn, for the first 4 seconds, the graph will curve up, and the next 2 or 3 seconds, the graph will curve down. That means, for the first 4 seconds, each second, the car covers more distance than the previous second. That's the curving up. For the next few seconds, each second, the car covers less distance than the previous one. You can see the curve, it's curving down. Alright. Now, since this is not a straight line, you can see curves up and then curves down. Now, how do we find the rate of change in such a case? You see, the rate of change does not remain a constant. The rate of change keeps changing, because when t changes by 1 unit, the change in the output is not the same in the first second, in the second second, the third second, and so on. The rate of change is no longer a constant. So let's take 2 points, 2 positions of the car. So points A and B represents 2 positions of the car at times t1 and t2. This is position A, and this is position B. And position A corresponds to time t1. Position B corresponds to, alright, we would say that position is y1. When the car is at point A, the position we call y1. That means at time t1, the car is at position y1. and the car is at B at time t2, and the position we will say is y2. Alright, so what is t2 minus t1? t2 minus t1 is this quantity, and we represent it by that length, and that is our delta t. This is the change in the time. Now, during this change in time, how much did the position change? Well, the change in position of the car during this time interval is y2 minus y1. That is this distance, and we call that delta y. Now tell me, in the case of the straight line graph, we said delta y by delta t is a measure of the rate of change. Now, if you take delta y by delta t here, does it give you a measure of the rate of change in that interval? No, it will not, because the change in position is not along a straight line. If it is along a straight line, then the rate of change will be delta y by delta t. Now, but we can do one thing. We can measure the slope of the straight line AB. If you join the line AB, we can measure the slope of that line. The slope of this line will be delta y by delta t. That's right. Now, we can say slope equal to delta y by delta t. Now, what is the physical significance of that? What does it actually mean? Now, this line AB is very often called the secant line of this curve. So, if this is the curve AB, then the line AB is called its secant line. So, delta y by delta t is the slope of the secant line joining points A and B. Now, what does slope of the secant line actually represent? If you now take the change in position of the car during a time interval delta t, this delta y by delta t actually represents an average change in position of the car. You see, the change in position doesn't remain a constant, but you can find an average change in position. So, what does the slope of the secant line AB represent? It represents an average change of the position y with respect to t in that time interval delta t. That means, in a situation like this where the change is not a constant, delta y by delta t does not give you the rate of change, but we can say it represents an average rate of change during this time interval, the average during that time interval. Now, the actual rate of change in such a case, the actual rate of change in a case like this has meaning only at one point, because as you put your foot down, at each point along the path of the car, the rate of change is different. So the rate of change has a meaning only at one point. What is the rate of change at A? The moment you move to B, the rate of change is different. You move to C, the rate of change is different. You move to another point, the rate of change is different. So the rate of change has meaning only at a given point in such a case. Now, the rate of change at the point A, we can find the rate of change at the point A if we make this time interval very small and let the time interval come so close to zero that we can say for all practical purposes that time interval is zero. That means as the time interval becomes smaller and smaller, this point B will come closer and closer to A. Is that right? That means this secant line will almost become the line representing the curve itself at that time. So what we will do is, let's take point B over here. What we are doing is, we have now reduced the time interval. The delta t, previously the delta t was this. And now we take delta t much smaller. That means if this is position A, this is position B. And you can see the secant line and the curve itself, there isn't a lot of difference in there. They are almost the same there. Now, at the instant when delta t is very close to 0, we say the point B is almost at the point A. If you now bring B again closer and closer so that B is here, there will be no distinction between the secant line and the curve itself. And the line then becomes a tangent line at the point A. Is that right? Now, that is very important to know. That is, if I bring the point B, say here, then AB, the line AB and the curve AB will not be distinguishable. And the line then becomes almost a tangent drawn at A. Now, like this. That's right. So, delta y by delta t now is the slope of the tangent line. Now, when you say now, what does that now means? Now means when B is very close to A, so that the time delta t is very small, very close to 0. When that delta t is very close to 0, or we talked about limiting value, didn't we? So the limiting value of delta y by delta t, when this delta t is very close to 0, the line AB actually becomes the tangent at the point A. Then the rate of change at A will be the slope of that tangent line. You see how the secant line becomes the tangent line? How does the secant line becomes the tangent line? By bringing this point B closer and closer such that the time interval delta t becomes very small. So the slope of the tangent line at A represents the rate of change at A. That means the rate of change at A is the rate of change at the instant when the object is at A, or at the instant t1. So the slope of the tangent line is called the instantaneous rate of change. And this is a measure of the derivative of the position function. You see, the derivative of the position function, like this, has a meaning only at one point, and it is called the instantaneous. At that particular instant, what is the rate of change at t equal to t1? It is the slope of the tangent line drawn at A. What is the rate of change at the instant t equal to t2? It is the slope of the tangent line at the point B. Now, if you are watching my pointer here, you can see the slope of the tangent line at A is positive. The slope of the tangent line at B is negative. What does that mean in the case of the motion of the car? At A, each time the time increases by 1 unit, the position is increasing. And that's the meaning of a positive slope. At B, with time, the position is decreasing. And you've got a negative slope there. So, again, what is the definition of derivative for a function like this? The slope of the tangent line at the point A is called the instant